All right, let's take a look at today's lesson. So today we're going to be looking at extreme value problems. This topic in calculus we call optimization problems, and for some students optimization problems are one of the more difficult topics for us in calculus. So the more practice we get, the better. We will be using, in some instances, calculators. But let's kind of talk through what's going on. We have a global, that's an absolute. We've talked about absolute maximum and absolute minimum values before. Another word for that is global, a global maximum or a global minimum. If the function is continuous on a closed interval, then the function will have a max, an absolute max, and absolute min. It's like a theorem for us. It will happen. And so where could that happen? Where could we have the max or min? Well, it could be at the endpoints. That's an option. It could be where the first derivative is 0, or it could be where the first derivative is undefined. These are all three options that we have for finding our absolute extrema. And we'll have a few examples where we walk through that, and I'll show you how to do that. So this is just words, so maximizing or minimizing. When we are finding global maxes or mins, we are saying that we're maximizing or minimizing. The reason this wording is important is because the problems that we're going to face are word problems, and in order to figure out what it's asking us to do, these are kind of the key words to look for. If it says maximize something or minimize, or maybe it says closest, we want to be closest to a point, those kinds of words tell us that we're working on an extreme value problem or an optimization problem. And so let's just look at this function, for instance. This function is on a closed interval. Okay, this closed interval. Our absolute maximum value is 65. Okay, that happens to be on an endpoint, but it is the absolute maximum value. It's the very largest that that function gets. And our absolute minimum value would be -16. This does occur where the first derivative is 0. So this situation, this absolute maximum would be like this, like number 1. It's where it's at the end of the interval. But the absolute minimum of -16 would be where the first derivative is 0. So see, it's kind of it just depends on what you're dealing with. You could have one of each in there. Okay? So questions so far on the concept. Alright, so let's go to, we have just a couple of examples to work. And of course they're word problems. So let's look at the first one. Congruent squares are cut from the corners of a 1 meter square piece of tin, and the edges are then turned up to make an open rectangular box. How large should the squares cut from the corners be in order to maximize the volume of the box? Okay, so I have to draw a picture. So these are the little squares we're cutting out. Okay, so we are wanting to maximize volume. That means that we need to come up with an equation for volume. That's what we're focusing on. We're going to maximize the volume. So with this information, we need to write an equation for volume. Of course, we do need to know all of our volume equations. For a rectangular prism, it's length times width times height. Okay, so just kind of write that there to make, help us think. So this portion right here, that is going to be, you can call it length. That'll be the length. And this whole piece is 1 because it's 1 meter square, right? So this whole thing is 1. So to get to this, it would be 1 minus x, right? 1 minus 2x. So this portion is 1 minus 2x. Does that make sense? We okay with that? Okay. Likewise, we look at this as the width. This also, it's a square, so this is 1 minus 2x. Okay, so let's kind of fill in our equation. So our length is 1 minus 2x, our width is 1 minus 2x, and our height, once we turn these edges up, you see our height is going to be x. Okay, so this is the equation that we're going to be dealing with. so one important thing for us to see if we can find the domain. We really like working these problems with endpoints. It's not always possible to get an endpoint, but we really like working them with endpoints. So let's see. We know that 0, right? I mean, it can't be smaller than 0 because that doesn't make any sense to have a length smaller than 0. So 0 would make this 0. What would make these 0? 1/2. So basically our domain is between 0 and 1/2. Okay, so this one does give us endpoints. It's kind of nice. I'm working one, the first one has endpoints and it behaves kind of nicely. This one is a little different, but this one we're just working it like we would. So what would we do? We have our domain, we have our function. We really need to like multiply all that out and get it much easier because we're going to have to take the derivative. Okay, we're going to be using product rule to take the derivative. So I just FOILed it out and then multiplied by x. Hopefully we're okay. I'm just going to write what we got, which would be 4x cubed minus 4x squared plus x. Okay, so that's our volume equation. All right. So what we want, this is called the candidates test. Okay, this is a really big deal in calculus. We work on that. We know we're going to check our endpoints. Okay, we're going to check the endpoints. These are our x values. These are our volume values. Okay, so if you recall on the other slide, we said that the extrema could happen at endpoints, right? Here's my endpoints. Where else could the extrema happen? Where the first derivative is 0. Right? Or where the first derivative is undefined. So let's find the first derivative and let's talk about it. Okay, so v prime, so we would get what, 12x squared minus 8x plus 1. I'm just using the power rule. Just using the power rule. So is there anywhere that this derivative is going to be undefined? Is there any x value I'm not allowed to use? No. So really all I need to worry about is where it's 0. Okay, I don't need to worry about the third, little, I think it was part C on the other page where the first derivative is undefined. We don't have that scenario here. But we are going to set it equal to 0 and see what's going on. So this is actually factorable. And it factors to 6x minus 1. And 2x minus 1. So x could be 1/6 or x could be 1/2. And we already have 1/2 up there. So our other value to go on our chart is 1/6. This is called the candidates test. Okay? And I'm just testing all the candidates. I mean, it makes sense. I'm going to test the endpoints. I'm going to test my zeros from the derivative and my undefineds from the derivative, and that's how I'm going to determine who is the biggest value and who is the smallest value. So it's the volume that we're maximizing. These numbers, we're going to plug these numbers into volume. That's where these are going to go. These are going to go back to our volume equation. Okay, we're going to plug them right in there and see who is the winner. So when I put a 0 in here, I get 0. When I put a 1/2 in here, I actually get 0. So, well, not really making much headway. So it looks like 1/6 is the actual, the value that's going to maximize the volume. So if I put a 1/6 in there, I get 2/27. So this, we circle and we say this is the max. And that's what we do. Circle it, say that's the max. Now let's see what question they want us to answer. Alright, how large should the squares be cut from the corners in order to maximize the volume? So they just want to know what x is, don't they? That's all. So x is 1/6, and we always need to put units if we have it, and we do 1/6 meters. So that's the answer to the question. Okay, so that is a straightforward, typical optimization problem. We read the problem, we come up with an equation that models the problem. We get the equation down to one variable. We only can have one variable here. we already had one variable, we didn't have to worry about that. Then we take the derivative, find the domain, test the endpoints and the derivative, and we got it. Okay? That's the procedure. Alright, so the next one, let's look at the next one. We have a manufacturer produces cardboard boxes with square bases. The top of each box is a double flap that opens as shown. If the bottom of the box has a double layer of cardboard strength, if each box must have a volume of 12 feet cubed, what dimensions will minimize the amount of cardboard? Okay, volume and minimizing the amount of cardboard, those are two different things, right? That's not the same thing. Minimizing cardboard, we would need to work on surface area, not volume. So they gave us volume for a reason. We don't really know why yet. We'll discover why, but we don't know why. So we just need to kind of focus on what we're supposed to minimize or maximize. Okay, that's what we're focusing on. We're focusing on the amount of cardboard. So we need an equation for the amount of cardboard. That's what we need. And we're going to use this diagram to get that equation. So I called it C of x for cardboard. I mean, you can call the equation whatever you want. We know that the bottom is doubled. So I'm going to need 2x squares, plus I have the top, right? Then I have the sides, will be x times h, and how many sides do I have? I have 4, right? 4 sides, so plus 4xh. And there's my representation for cardboard. Now notice that I have more than one variable. Okay, that's a problem. I can't have more. I have to only have one variable because I've got to do everything I did over here. I've got to take the derivative and do all that stuff. I can't with like this. So there has to be additional information that we can use to find, to get rid of one of the variables. I call it our helper equation. It's a helper equation. Here's our main equation, and we must have a helper equation somewhere embedded in these words that are going to help us get down to one variable. Alright, so let's go back and look at the volume. They talked about volume, and it was like, why do they give us volume? Well, that's our helper equation. Okay, so let's figure out how we can use volume to help us narrow it down to one variable. So let's just kind of write the volume. So volume equals, and I'm going to use these in terms of these variables. So it'd be x times h, so x squared h. So that's a representation for volume of this particular box. So we're told that volume has to be 12 feet cubed. So I'm going to replace v with a 12. You see how this little equation is going to be a little helper to us, right? I would like to get rid of the h over here because there's just one of them and there's two different x's. So I would actually like to solve this for h so I can eliminate h over here. So that's what I'm going to do. I'm going to divide both sides by x squared. And so I'm going to get h equals 12 over x squared. So here's our little helper equation. It's helping us get rid of a variable. So I'm going to take this information and I'm going to replace h with 12 over x squared. So c of x equals 2. Actually, it's 3x squared. 2x plus 1x is 3x squared plus 4x times 12 over x squared. Okay, so c of x equals 3x squared. So let's work on this. That's 48. And it really would be 48 over x, right? That's what it would be, simplified 48 over x. But I would like to use the power rule instead of doing definition of the derivative. And so instead of writing 48 over x, I'm going to write it as 48x to the negative 1. Are we okay with that? Just 48x to the negative 1. The reason being, I want an easier time to take the derivative. This will be easier for me. I can use the power rule on this. Okay, I can't use the power rule on 48 over x. Okay? So, let's look at domain. This one is, x is bigger than 0. We really can't pinpoint it, or it would be very difficult to pinpoint the end of this domain. And let's think about what the domain is telling us. If x were really close to 0, the bottom would be like really tiny and it'd be really tall, right? Or if x was as big as possible, the bottom would be really big and the height would be really small, neither of which make any sense as to maximizing volume of anything, right? Or actually maximizing or minimizing the amount of cardboard. If you have a gigantic, that is not going to minimize cardboard. That would be using a lot of cardboard. So in this particular case, we really we can't test endpoints. It would be more work than would be useful to find the other endpoint here, because it really practically doesn't make sense. Are we okay with that? So instead we're going to divert. We're going to do a little bit of a different way, and so we don't really have endpoints to check, but we do have critical numbers to check. And so actually let's find our derivative. Let's determine our critical numbers. So I have 6x minus 48x to the negative 2. All right. So is there a place where this derivative is undefined? Yes, there is, isn't there? What value is it undefined? At 0, right? Because this is really 48 over x squared, right? 48 over x squared, right? If I put a 0 in there, that's bad. So is 0 going to be a valid answer to this? No. No. I mean, if x is 0, we don't even have a box, right? We don't even have a problem with it. No, we cannot make x 0 to make the problem go away. Sorry. If x is 0, we just don't even have a box, so we can't do with that. But we can set the derivative equal to 0. So 0 equals 6x minus 48 over x squared. I'm going to put it back in normal form because we're getting ready to solve. What I would do is I would move this to the other side. 48 over x squared equals 6x. And I would cross multiply. That's how I would solve it. There are many other ways to solve this. This is just what I would do. So I have 6x cubed equals 48. X cubed equals 8. X equals 2. Really, we only have one critical number. That better be the answer, right? We're in a little bit of trouble. And I'm always skeptical. I just am. I always want to test it. So I'm sure that's probably the answer, but here, how can we test it? Well, we could do a sign chart, right? We could do a sign chart and we could test it. I would, if I were you, just to make sure. So we test it from our, from our derivative, where we got the number from. Notice that when we did candidates test, did we go back to the derivative? No, we went to volume, right? Candidates test is different than a relative extrema test. Here, we're just making sure that we're thinking correctly. And then if I put, let's see, if I put a 1 in here, I get a negative number. If I put a 3 in here, I get a positive number. So this is going down and then up. What does that tell us? That we were correct, right? X equals 2 is the value that minimizes the amount of cardboard used. So this is a minimum. Now let's answer the question. We know x needs to be 2, so 2 feet by 2 feet by, and we need the height. How are we going to find the height? Yeah, we're just going to plug it back in over here, right? It would be actually more convenient to put it in here, or very convenient, because it's already solved for h. Right, if I put a 2 in here, 12 over 2 squared, or 12 over 4, would give us 3. And there are the dimensions that minimize the amount of cardboard that we use. Okay, that has the volume that we want of 12 feet cubed. All right, questions on that? Okay.